In the last video, we saw this notion of a dual of an LP. So we were given an LP in this particular form. We called it the primal, the LP with which we started. And for this LP, we associated this one, which we called the dual. So we will continue seeing a little bit more about primals and duals. So in this lecture, we will see two things. So if I start with the dual LP as a primal, what would its dual be? That is part 1. And in part 2, we will consider different forms for the primal. Suppose we start with primal and not in this particular form. How can we write the dual without having to explicitly write it back to this form? We will see some shortcuts to write the dual. So that is part 2. So the reference for this video is section 6.2 of the text. So let's start with part 1. Dual of the dual. So we have this LP, minimize B transpose Y, subject to A transpose Y bigger than C, Y bigger than or equal to 0. Now suppose the feasible region of this LP is, say, some region R, okay, and say the optimum is either unbounded or some gamma for this particular LP, okay. Now let's make a transformation. Suppose I rewrite the constraints as minus A transpose Y less than or equal to minus C, Y bigger than or equal to 0, and then I am not changing the objective. So now what happens? Well, the feasible region remains the same. The set of all y's that satisfies this constraints or these constraints is the same. Now what about the optimum? The optimum is the same. It is either unbounded if this LP is unbounded, or it is gamma. So essentially nothing changed, okay. Now suppose I change the objective to a maximization problem. So instead of writing min B transpose Y, we write it as max of minus B transpose Y subject to these constraints. Now note that the feasible region is still the same, and if the optimum was unbounded before, it is going to be unbounded. But if the optimum was some gamma, then the optimum of this LP would be minus gamma, okay. So when you reversed the min to max and the B transpose to minus B transpose, essentially what are we doing? Like the original LP was a minimization problem. So suppose the optima was gamma like this. Now what did we do? For every Y, so here there is B transpose Y, the minus B transpose Y would be here, and then we are maximizing over minus B transpose Y, and the optimum will be minus gamma. Okay. Now this LP is in the form of the primal that we saw last time. So what is the dual of this? The dual of this would be min of minus C transpose X. So now suppose we multiply with variables x1, x2 till xn to the constraints. So the variables are xi's, and now this part is here. Now what about the constraints? It will be minus a x bigger than or equal to minus b. Okay, and x bigger than or equal to 0. So this is essentially, if this is the primal, this is going to be the dual. Okay, now what can we say about this? This will have some feasible region R prime. Okay, and the optimum could either be unbounded or some gamma prime, but then if we use the duality theorem, this gamma prime would just be minus gamma, because the duality theorem says that the primal and dual will have the same optimum when they exist. Okay, fine. So now we have this. Let's do some more transformations to this. So I rewrite this thing as it is, min of minus C transpose Y, but this is just going to become Ax less than or equal to B, x bigger than or equal to 0. So again here the feasible region does not change and the optimum also does not change. Okay. And finally, now I will make another transformation, which is changing min to max of so here this has to be x. So max of C transpose X with Ax less than or equal to B, x bigger than or equal to 0. Note that in this transformation, the feasible region remains the same. However, the optimum will change sign. Okay. So now notice that what did we do? We made a transformation here. We did the dual here. And then we made transformations here. And we got back this. Essentially, in order to write the dual of this, we rewrote it in a form which we know already, and we took the dual and then we wrote some kind of an equivalent LP. The only thing to note is that the signs change. Okay, but then here again the signs did change, and now we got back the previous gamma. Okay, so this gives us the dual of this. So this is to say that the dual of the dual is actually the primal in some sense. Okay, so let's see a different way of looking at it. Consider this minimization problem. Now, suppose we directly think of multiplying these constraints by some variables x1, x2 and then adding it up. What do we get? We will get 4x1 plus 8x2 times y1 plus 2x1 plus x2 times y2 plus 3x1 plus 2x2 times y3 this thing is bigger than or equal to 2x1 plus 3x2, right? Now this, we can write this as long as x1 and x2 are bigger than or equal to 0. Okay, now note that we want to minimize this quantity. Now if this thing is less than or equal to 12, so let me write it. 4x1 plus 8x2 is less than or equal to 12. This thing is less than or equal to 3 and this thing is less than or equal to 4. Then what happens? 2x1 plus x2 less than or equal to 3. 3x1 plus 2x2 less than or equal to 4. Suppose we know that, then since y1, y2 and y3 are all positive, if we have something bigger than these, then that quantity has to be bigger than this quantity. So in some sense, this cost should be bigger than this. So let me write that. So if we have these constraints, we have the cost 12y1 plus 3y2 plus 4y3. This quantity is greater than or equal to this thing. Okay, and this thing is going to be bigger than or equal to this. So then what do we have? This quantity gives a lower bound on the required cost. Okay, now if gamma is the optimum of this LP, now this 2x1 plus 3x2 will lie somewhere here for different values of x1, x2 that satisfy these equations. Okay, now as you vary x1 and x2 along this set of constraints, you will get various values for this particular function, and they will be less than, they will be at most gamma. Okay, now what we want is, we want to maximize this quantity so that we can reach gamma. So this gives us an objective: maximize 2x1 plus 3x2. Okay, so if you check the previous video, we started with this LP and we wrote the dual and it led us to this. Now when we start from here and do a symmetric argument, just that now it's a minimization problem, so we get to the optimum from below, we get back this LP. Of course there are these constraints: x1, x2 bigger than or equal to 0. Okay, so in some sense these two LPs are tied to each other. Okay, so this if you start with this primal, you get back this dual, this LP as a dual. Now if you start with this as your primal, you will get back this as your dual. So essentially these two are primal dual pairs. Okay, let me just write it. So here is the message of this part of the video, which is the fact that these two LPs are called primal dual pairs. Okay, so now we move on to the next part where we will see how to write the dual for various other forms. Here there was a specific form. We will try to write the dual for different forms. So we will explain this with an example. So this is the original thing that we had from before. Now let's make the first change. Instead of having a less than or equal to, suppose we had a bigger than or equal to. So consider this LP. Here we have bigger than or equal to 12. In order to get the dual, what we could do is we can multiply this entire thing by minus and rewrite it as minus 4x1 minus 8x2 less than or equal to minus 12, and then do the same thing. The other way is that the y1 that we multiplied with here, we kept it to be positive. Instead, here we will multiply it with a y1 which we can ask to be negative. Okay, this gives us the following dual. Everything is the same except that now you will say y1 less than or equal to 0, y2 and y3 are the same as before. Okay, note that whenever we have a bigger than or equal to sign instead of this less than or equal to, those corresponding variables have to be made y1 less than or equal to 0 and the rest can remain the same. That gives us the dual. Okay, now what if this one is equal to? Now we have to rewrite this into less than or equal to and bigger than or equal to. Okay, so 4x1 plus 8x2 equals 12. So this means this along with minus 4x1, rather 4x1 plus 8x2 bigger than or equal to 12, which translates to minus 4x1 minus 8x2 less than or equal to minus 12. Okay, so now we have 4 constraints and then we will multiply with, let's call it y1 plus, y1 minus, y2 and y3. Okay, now on the dual side we will now have y1 plus, y1 minus, y2, y3. They are all bigger than or equal to 0. Okay, and then the coefficient of x1 would be what? So let's erase this. The coefficient of x1 would be 4y1 plus minus 4y1 minus plus 2y2 plus 3y3, and then it has to be bigger than or equal to 2. 8y1 plus minus 8y1 minus plus y2 plus 2y3 is bigger than or equal to 3. And then what happens to the objective? it becomes 12 into y1 plus minus y1 minus. Okay, we can rewrite these two things as 4 times y1 plus minus y1 minus and 8 times y1 plus minus y1 minus, and this also is 12 times y1 plus minus y1 minus. Now what if we call this variable as y1? Now clearly we can replace, so what we are going to do is set y1 equal to y1 plus minus y1 minus. So in this case, this can be rewritten as, let me cut it, strike it through, and we get 4y1 plus 2y2 plus 3y3. So let me erase this to make it a bit clear. And this one gets erased to 8y1 plus y2 plus 2y3, and this thing gets erased and becomes 12y1. Although note that there is a crucial difference. Here we had y1 bigger than or equal to 0, but now y1 plus minus y1 minus can be any value. It could be non-negative as well. Okay, so because as you vary y1 and y1 minus, this y1 plus minus y1 minus can either be positive, negative or 0. So this is the main change. We just say that y1 is unconstrained. So essentially, whenever there is an equality here, we started off with an equality here, right? The corresponding y1 should be unconstrained. So far we have seen two things. If this thing is bigger than or equal to, the corresponding y1 is less than or equal to 0, and if this thing is equal to, then the corresponding y1 is unconstrained. Okay, so this gives us two things. Now we will make another difference, which is what if x1 is not constrained to be positive. Okay, so this gives us this LP. x1 is less than or equal to 0 and x2 is bigger than or equal to 0. So now if we ask for the dual, the main thing to note is, how do we compare the coefficient of x1 with the cost? See, as usual, we multiply these things with y1, y2 and y3. Since all of them are less than or equal to, we will keep y1, y2, y3 bigger than or equal to 0. But now, what is the coefficient of x1 here? This will be 4y1 plus 2y2 plus 3y3. Now when x1 was bigger than or equal to 0, we wanted this thing to be bigger than or equal to 2, right? And then that was giving us an upper value. But now when x1 is negative, so this times x1, so let me write it. So this times x1, we want it to be bigger than or equal to 2x1, right? But when x1 is negative, the required inequality will happen only when this thing is at most 2. Okay, so this gives us So this gives us this constraint 4y1 plus 2y2 plus 3y3 is less than or equal to 2. Since x2 is bigger than or equal to 0, the other constraint remains the same. 8y1 plus y2 plus 2y3 bigger than or equal to 3, y1, y2, y3 bigger than or equal to 0. And of course, the objective is the same, minimize 12y1 plus 3y2 plus 4y3. So note that when you have something to be negative, the corresponding constraint here becomes less than or equal to 2. Okay. Now the next question is, what happens if there is no constraint on x1? Okay. So x1 is unconstrained. So let us try doing this now. x1 unconstrained. So the trick here is to write x1 as some x1 plus minus x1 minus. Okay. Now, so on doing that, what do we get? We get this LP. So note that we made this change so that we can ask for x1 plus and x1 minus to be bigger than or equal to 0. I mean, if you see, if x1 was 5, we can put x1 plus equal to 5 and x1 minus equal to 0. And if x1 was minus 5, then we can put x1 plus is equal to 0 and x1 minus is equal to 5. Okay, fine. Now from here, if we do the same things as before, like you multiply this with y1, y2, y3, now we will have an extra comparison, right? See, this thing will remain here, this thing will be corresponding to this, and this comparison will correspond to this, and in addition there will be this comparison, which is, so let me write all of them. So we have 4y1 plus 2y2 plus 3y3 bigger than or equal to 2 minus 4y1 minus 2y2 minus 3y3 is at most minus 2, and then we have 8y1 plus y2 plus 2y3 is at least 3. So sorry, before I should have said at least. Okay. Now if we combine these two, we get, so combining these two will give us 4y1 plus 2y2 plus 3y3 equal to 2. Okay, so this gives us the dual, which is, let me rewrite the dual. The objective is the same. Okay, so what is the thing? If we start with something which is unconstrained, the corresponding cost equation will have an equality here. Okay, so let me summarize whatever we saw in these 4 cases. So normally these two are the primal dual pairs. Now what did we see? Suppose one of the constraints has, say the ith constraint has bigger than or equal to, so it will look like ai, say the ith row bigger than or equal to bi. So normally it has to be aix less than or equal to bi. So ai is the ith row of this matrix. In that case, the yi has to be less than or equal to 0. The yi that we multiply with has to be less than or equal to 0. Now if we had aix equal to bi, then yi is unconstrained. Similarly, now if we had xj to be negative, then the corresponding constraint here, which will be A transpose jy, should be less than or equal to Cj. And finally, if we have xj unconstrained, we should have the corresponding constraint here, which will be A transpose jy will be equal to Cj. Okay. Now, in fact, if you start from this as your primal, then this will be your dual. And here, suppose we had yi less than or equal to 0, then the corresponding thing here has to have bigger than. Here, if we have yi to be unconstrained, the corresponding constraint here should have equality. And here, if the constraint is less than or equal to, then the corresponding variable should be negative. And if here you have equality, the corresponding variable should have unconstrained. So we saw an example where we went from here to here, but going from here to here is also symmetric. So now let me finish with one example. So consider this example. So it's a maximization problem. So there are 2 constraints. So there will be y1 and y2. So first of all, note that this thing is bigger than or equal to and this thing is equality. Now if this thing is bigger than or equal to, the corresponding yi has to be less than or equal to 0. So we will have y1 less than or equal to 0. And this thing is an equality. So y2 will be unconstrained. So y2, unrestricted, unconstrained, we can use interchangeably. Unconstrained. Okay. Now, how do we write the constraints for the dual? First, let's write this. So, write the left hand side. It will be y1 plus 5y2. And we have to compare it with x1. But since x1 is less than or equal to 0, the corresponding thing here should be less than or equal to. So we get less than or equal to 8. Now what about y2? Minus 6y1 plus 7y2. And here x2 is bigger than or equal to 0. So we have to maintain it as bigger than or equal to 3. And finally for y3 it will be y3 minus 2y2. Now here x3 is unrestricted. So you have to equate it with minus 2. Okay? And then the maximization becomes a minimization. The right hand side of these inequalities, which will be 2y1 minus 4y2. Okay? So also you can verify that if we had started with this and performed these changes, we would get back this. Okay? So this brings us to an end of this video. The main message is to consider this primal dual transformation shortcuts.